Today what I want to do to finish off this unit about electrostatics is do a little bit of work with some numbers. We're not going to get too calculation based here, but here we go. Let's say I have a metal sphere, and I know that metal sphere is negative. But let's say I know more specifically that the sphere has, let's say, 200 excess electrons. So what does that mean, 200 excess electrons? That means that, let's say there's 1 billion electrons normally on this, therefore there's 1 billion protons normally on this because objects are normally neutral, but that I've added an excess of 200 electrons. So what would be the charge of this object? Well, Q being the symbol for charge, we would say it has a charge of negative 200 E. E is the what is called the elementary charge, and it has a certain value. We're not going to care really too much about that value, but that value is 1.6 times 10 to the negative 19th coulombs, which is the charge on both the proton and the electron, whereas the proton has a positive value of this, the electron has a negative value of this. But this is just so much more convenient than this ridiculous number. So this thing has a charge of negative 200 E, an excess of 200 electrons. Okay, so I don't know why I drew that so big. Let's say we had something that had a Q of positive 64 E. What would that mean? Well, the positive means that this thing is missing electrons. So it's missing electrons. How many is it missing? It's missing 64 electrons. Okay, that's how this goes with the number. If something is negative, it has an excess of electrons, something's positive, it is missing electrons. So let's use that as a basis for what we're going to talk about. So if I have an object who has a charge of negative 20 E, and let's say I have another object that's a charge of 0, it is neutral. Okay, and I create a bridge between them, or I touch them together. Well, what's going to happen? Well, we know that charge wants to move from regions of high electron concentration to low electron concentration, right? This is like a charging by conduction process. Therefore, this object, which is negative 20 E, has an excess of 20 electrons. This has a balance of electrons. Electrons are going to want to move in this direction so that these things are all, like the excess electrons are all exerting repulsion forces on each other. They want to minimize those repulsion forces. In order to do that, some of the electrons are going to escape over to here. How many? Well, if these two objects are equally sized, let's say equally sized, and they're both conductors, what's going to happen in this is we're going to end up with a situation in which each of them has negative 10 E, because then the distribution of charge here, they both have equal concentrations of excess electrons. That's as far apart as the electrons can get, so that's as good as it can happen. So what happened to cause this? Well, electrons flowed from this object to this object until they got to this charge distribution. So how many electrons flowed? Well, it looks like 10 electrons flowed. Right? Notice, remember, this is the symbol for electrons. That's the symbol for the elementary charge. Well, let's look at this again with, let's say something has a positive 40 E charge and a neutral, and I connect them. What happens here? Well, this thing is missing 40 electrons. This has its full complement of electrons. So in this case, electrons are going to travel in this direction across the bridge until they have equal concentrations of charges. Once again, equally sized, and they're both conductors. How many electrons moved over? Well, it must have been 20 to get that. What I want you to notice here is that's my system. What's the net charge on the system? Well, 0 plus negative 20, the net charge is negative 20 E. What's the net charge here? Negative 10 and negative 10, it's still negative 20. Notice in this process, the net charge of the system doesn't remain, net charge in the system remains constant. And that's because of the conservation of charge. Let's try one more of these. Okay, actually we'll do one other here. Let's say this has negative 16e and this has positive 8e. All right, so this has an excess of electrons. This has a lack of electrons. If I connect them, well, first off, what is the net charge on this system? Well, positive 16 or negative 16 plus 8. The net charge in the system is negative 8e, right? And so what's going to happen here is I'm going to have electrons go from the more negative thing to the less negative thing. So that's this direction. But what's going to be the final charge on this? Well, what's happening here is that net charge has to be distributed in a way that minimizes the concentration. If these two objects are equally sized, that concentration then is an equal amount. Boom, there you go. So how many electrons had to be transferred over? Well, if you notice this went from an excess of 16 to an excess of 4. It lost 12 electrons. This went from lacking 8 to having 4 extra. So lacking 8 to 0 to 4 extra, there's your 12 electrons, okay? Now, one last thing, we're not really gonna talk about this, but if I had a little object and a big object, and let's say this thing had negative 100e, and this thing is neutral initially, and I connected them, they wouldn't both end up with negative 50e in the same way, because I'd want equal concentrations of electrons. This smaller object, to have the same concentration, might only take, like, say, 5 of those electrons, and this ends up with negative 95. There's a mathematical way of determining that. But these things have equal concentrations because of the relative size. When we do this, we'll talk about equal sizes. Now, I'll just go back to the beginning one. So, here, notice that charge is going to flow from this object to this object. But eventually, that flow of charge will stop once they've reached an equilibrium. So, they're at an equilibrium when the charges, or the charge concentrations, are the same. Another way to say that is they are at an equal potential, right? Because charge is going to flow until, like that potential is related to potential energy. Things tend to go from high potential energies to low potential energies. And what nature is trying to do is sort of like even everything out. In the same way that if you raise something off the table and you let it go, that thing drops down because it's trying to go to lower potential energies. So the charge flow just stops after a while, right? We're not really going to talk about how long it would take for this situation to go to this one. But our next unit is going to be about electricity. And electricity is about this flowing of charge. We haven't really talked about the flow. We've only talked about the state of the object after the charge has flowed or before it flowed. But we're going to start talking about that flow of charge. But this would not be very interesting because that flow of charge would only last for a short period of time. So we're going to talk about is, well, what would have to happen in order for this thing to continuously have a flow of charge? Well, what would have to happen, if you think about it, is as charge gets from this thing to this thing, something would need to pull that excess charge off and place it here so that it went back. Place it here and went back. Place it here and went back. But we'll talk about that when we talk about our introduction to electrical circuits.